You know, we write code all the time, right? But do you ever stop and think about what's really going on under the hood? Today, we're going to go looking for a ghost in the code, that invisible mechanism that makes object-oriented programming tick. And that ghost, well, it's the pointer. So let's start with a really basic question, one you probably think you already know the answer to. When you create an object and assign it to a variable, what is that connection? What's that invisible string, that secret connection that holds them together in memory?
Okay, check this out. This is a super common bit of Java code. We make a new circle object, and we assign it to myCirc. Then we make another variable, myOtherCirc, and just set it equal to the first one. Simple, right? But what did we actually just create in the computer's memory?
So this makes you stop and think, right? What was the assumption you just made? Did we just clone the circle? Did we make two separate identical objects? Or is there something a little sneakier going on here? And boom, here's the big reveal. You only made one circle object. That's it. Your variables, myCirc and myOtherCirc, they don't actually hold the object itself. Nope. What they hold is the memory address of that one object. They're basically just two little signposts, or object references, as Java calls them, both pointing to the exact same spot in memory.
Okay, so if pointers are this fundamental thing, how did different languages deal with them? Let's start with Java's whole philosophy on this. I like to think of it as the automatic car. It's all about being safe, easy, and getting you where you need to go with as little drama as possible. See, in Java, pointers are kind of like the engine in that automatic car. You know it's there, but you never really have to touch it. It's all handled for you. When you type new, boom, memory is set aside. When you use that little dot to call a method, Java just automatically follows the pointer for you. And the best part, when you're done with an object, this thing called a garbage collector just swoops in and cleans up the memory. It's all happening behind the curtain.
All right, now let's shift gears completely. If Java is that safe, automatic family sedan, C++ is the manual race car. We're talking raw power, total control, top performance. But here's the catch. You, the driver, are responsible for every single thing.
Just look at the difference here. It's night and day. In C++, you have to explicitly say, this is a pointer, using that little asterisk. To use it, you use this arrow operator, which is literally you telling the computer, hey, follow this memory address. And the big one, the most crucial difference. When you're done, it's on you to manually free that memory using delete. Nothing is automatic. It is all right there in your hands.
And this is where that whole manual race car thing gets real. That delete command, it's not a suggestion. So what do you think happens if you forget? If you take out that memory and just forget to give it back?
Yeah, you get what's called a memory leak, and it's as bad as it sounds. That chunk of memory becomes an orphan. It's still being used, but since no pointers are pointing to it anymore, your program has no way to get it back. It's just gone. And over time, these little leaks add up. They starve your program of resources, and eventually, bam, crash. It can be absolutely catastrophic for long-running applications.
And this C++ obsession with control, it goes even deeper. You don't even have to use pointers for objects if you don't want to. You can create them on something called the stack, where they get cleaned up automatically when they're no longer needed. The whole point is, C++ gives you the choice. It hands you the entire toolbox and says, you're the expert, pick the right tool for the job.
Okay, so you're probably thinking, with all this risk, memory leaks, manual everything, why on earth would anyone choose this? Why bother with these explicit pointers? Well, because with great risk comes great reward, and pointers unlock the payoff, one of the most powerful, most dynamic features in all of object-oriented programming.
And that payoff has a name, polymorphism. This is the magic that makes software so incredibly flexible and powerful. It's the ability for one single type of pointer, just one variable, to point to all sorts of different kinds of related objects while your program is running.
So imagine you have a pointer, and its type is, say, list item star. Now, at one moment, that pointer could be pointing to a simple integer. A second later, you could make that same exact pointer point to a character instead. Heck, you could even have it point to a whole other list of items. One pointer, endless possibilities. That's the power we're talking about.
So how do you unlock this? How do you make this magic happen in C++? It all comes down to one single keyword. You just add this one little word in front of your method declaration, virtual.
That one word, virtual, it changes everything. It's a message to the compiler. It says, Hey compiler, don't you dare decide which print method to call right now. Instead, I want you to wait. Wait until the program is actually running. And at that exact moment, follow the pointer, figure out what kind of object is really on the other end, and then, and only then, call its specific version of print. This is what we call dynamic binding, and it is the engine that drives polymorphism.
So there you have it. Two totally different ways of looking at the same problem, each with its own pros and cons. And really, it's not about one being better than the other. It's about knowing your tools, right? So you can pick the right one for what you're trying to build.
So let's just recap real quick. You've got Java. Its philosophy is all about safety and convenience. The analogy is that automatic car, and its killer feature is garbage collection, which keeps you safe. Then you've got C++. Its philosophy is total control and raw performance. That's our manual race car. And its key features are that direct memory control and the powerful polymorphism it enables, but it comes with a lot more responsibility.
So what's the big takeaway from all this? It's this. Pointers are the ghost in the code. Whether they're hidden from you, like in Java, or they're right there in your face, like in C++, they're the fundamental mechanism that powers the most dynamic, most interesting parts of object-oriented programming. And if you really understand them, you understand how your code truly works at a deep level.
So I'm going to leave you with a final thought, a challenge. Now that you've seen the ghost in the code, now that you can recognize this pattern of a variable holding an address instead of the thing itself, where else in your own code, in the projects you work on every day, are these pointers hiding in plain sight, quietly making it all happen?